Hi there, you little rascals! We have now learned everything about scattering equipment and Rutherford's atomic model. Through that, Rutherford was able to disprove Thomson's atomic model. But do you remember what we told you in the last video? Oh yeah, that's right. Rutherford's atomic model was not totally perfect, so Niels Bohr's atomic model completed it. We will now show you the problem with Rutherford's atomic model and also Niels Bohr's discovery. Let's have a quick revision of Rutherford's atomic model. So, he found out that positive mass is located in a very small and limited space called the atomic nucleus. But the actual size of the atom is determined by the electron shell. The negatively charged electrons revolve in this shell. But Rutherford wasn't able to find out anything else with his scattering experiment. And what was wrong about it? Or to be more precise, what exactly was the problem with his model? Have you ever heard about emission or absorption before? These phenomena could not be explained by the model. Emission means that an atom emits light. The illuminated stars that we used to stick all over the ceiling when we were children are a concrete example of that. They used to shine so beautifully when it was time to slide into Betty Buys. Well, well, the good old times. And what is an absorption? Well, exactly the opposite. When light meets matter, it gets absorbed by it, or passes its energy onto matter to be precise. So how does Niels Bohr explain this phenomenon? His image of an atom looks like this. As per usual, we have a positively charged atomic nucleus. But this time, electrons do not revolve freely in the shell, but travel in certain orbits. Just compare it to our planets traveling in orbits around the Sun. Niels Bohr formulated a couple of postulates for his model. What was a postulate again? Postulates are kind of like basic assumptions that have not yet been proven. So get ready for postulate number 1. Electrons only travel in discrete orbits, exactly like planets and their orbits. If the planets or the electrons didn't travel in the orbit, it wouldn't be discrete. The second thing he claimed was that electrons can jump from one orbit to another. Energy is being emitted or absorbed in the form of electromagnetic radiation, light. But we will explain to you how that works exactly some other time. This model helped explain a whole lot more than those that came before. But was it perfect and flawless? Nope, because postulates could not be deduced from it. One can use the model as an explanation for many unanswered questions, but that doesn't have to mean that it is correct. The hydrogen atom was a concrete example for the problem. According to Bohr's model, the hydrogen atom was supposed to be a flat disk. That sounds really stupid. Also, the model only describes the behavior of hydrogen atoms and ions with only one electron. In the case of a multiple electron system, the model doesn't apply. Despite its weaknesses and contradictions, it is a good basis to get an idea of an atom. That is why Bohr's atomic model was developed further into the nuclear shell model. You will understand in a second why it is called the nuclear shell system. The model helped explain shared traits of elements in the same group. Here we will find our positively charged atomic nucleus again. But this time, the nucleus is surrounded by multiple spherical shells. Now our electrons are located in those shells. But the chemical property of an element only depends on its outermost shell. The model didn't explain how electrons moved around in their shells. It only stated that electrons are located in a cave, quote unquote, and that's it. Shells can only take a limited number of electrons. For now, it should be enough to know that the innermost shell, the K shell, can only take 2 electrons and all the others can take up to 8. Weirdly enough, The shells have been named starting with the letter K, so they are called K, L, M, N, O, P and Q from the inside to the outside. You can also see this in the periodic table. Let's look at a concrete example together. How do we draw nitrogen's nuclear shell model, for example? At first, we have to look for it in our periodic table, of course. We can see that nitrogen is in the 5th group and the 2nd period. We actually get a lot from this information. The periods tell us how many shells there are. In this particular case, there are 2. L is the outermost shell. The next thing we need is the proton number. Nitrogen's is 7. The proton number tells us the number of protons and the number of electrons. That means we somehow have to distribute 7 electrons to 2 shells. That is done by placing them from the inside to the outside. We're going to put 2 in the K shell because it cannot take any more than that. We then place the other 5 in the L shell, since the L shell and any shell after that can take up to 8 electrons. Et voila! We drew nitrogen's nuclear shell model. The outermost shell helps us guess how the element is going to react in most cases. Atoms always want their outermost shell to be filled, therefore would like 8 electrons to be in their outermost shell. That is also called the noble gas configuration. On our right, we have sodium as an example. For example, sodium would rather lose its outermost electron to reach the noble gas configuration than take 7 more. But let's not go deeper than that. The most important thing is that you are able to place the periodic table elements' electrons in the right shells according to the nuclear shell model. That is how you will detect the number of bonding electrons and will be able to predict how the element is going to react. And that's it for now. See you and take care.